In 2025, a telescope floating 1 million miles from Earth detected a molecule in the atmosphere of a distant planet. A molecule that, on Earth, is produced only by living things. It is not proof of life, not yet, but it is the closest we have ever come, and that was only one of its discoveries. Welcome to Streamberg Space Stories. If you're new here, this is a place for long, quiet journeys through the science and mystery of space. Tonight, we're going to talk about a machine that has, in just a few years, changed what we thought we knew about the universe. Not slightly, fundamentally. It has found galaxies that should not exist, black holes that grew too fast, water where no one expected it, and possibly the chemical fingerprint of biology on a world 124 light-years away. This is the story of 5 discoveries made by the James Webb Space Telescope. So settle in. Let your breathing slow. Some of what follows may keep you awake a little longer than you planned. The James Webb Space Telescope launched on Christmas Day 2021 aboard an Ariane 5 rocket from French Guiana. It was the most expensive scientific instrument ever built, costing roughly $10 billion and taking more than 25 years to design, construct, test, and launch. It travelled for a month to a point called L2, the second Lagrange point, roughly 1 million miles from Earth in the direction away from the Sun. There, balanced in a gravitational sweet spot where the pulls of the Earth and the Sun combine to create a stable orbit, it unfurled a sun shield the size of a tennis court, 5 layers of reflective material, each thinner than a human hair, designed to keep the telescope's instruments in permanent shadow. On the sunlit side, the shield reaches temperatures of 230 degrees Fahrenheit. On the instrument side, it drops to nearly 400 below zero. The temperature difference between the two sides is over 600 degrees, separated by a few feet of layered foil. Its primary mirror, 21 feet across, is made of 18 hexagonal segments of gold-coated beryllium, each one polished to a precision of a few millionths of an inch. The gold coating is not decorative. Gold reflects infrared light with extraordinary efficiency, and infrared is what JWST was built to see. Infrared light passes through the dust clouds that obscure newborn stars. It carries the stretched, reddened signal of the most distant galaxies, whose light has been travelling for so long that the expansion of the universe has shifted it from visible wavelengths into the infrared. To see the beginning of the universe, you need to see in infrared. And to see in infrared, you need to be cold. Very cold. Cold enough that the telescope's own heat does not drown out the faint signals it is trying to detect. That is why JWST is where it is, 1 million miles from the warmth of our planet, floating in the dark, listening for light that is older than the Earth. The deployment was one of the most nerve-wracking events in the history of space science. The telescope was too large to fit inside any rocket fairing in its operational configuration, so it had to be folded. The mirror was hinged, the sun shield was pleated, the entire structure was compressed into a package small enough to ride atop the Ariane 5, and then, once in space, it had to unfold itself. There were 344 single points of failure, 344 mechanisms, latches, motors and hinges, any one of which, if it failed, could have ended the mission. The unfolding took 2 weeks. Engineers at the Space Telescope Science Institute watched each step in real time, knowing that the telescope was already too far away for any repair mission. Hubble could be serviced by astronauts. JWST could not. If anything went wrong, it was over. Nothing went wrong. Every hinge latched, every segment aligned, every layer of the sun shield deployed, the mirror locked into focus. And when the first calibration images came back, even before the science program had officially begun, the astronomical community realized that JWST was not merely as good as hoped. It was better, sharper, more sensitive, capable of seeing things that even its designers had not dared to promise. The universe, seen through Webb's gold eye, was deeper and stranger and more detailed than anyone had expected. Discovery 1. The galaxies that should not exist. According to the Standard Model of Cosmology, the most successful scientific framework ever constructed for describing the large-scale history of the universe, everything began 13.8 billion years ago in a hot, dense state. For the first few 100 million years there were no stars, no galaxies, no light, except the fading afterglow of the Big Bang itself, which cooled and stretched into the cosmic microwave background that we can still detect today. The universe was dark. It was filled with a cooling fog of hydrogen and helium, slowly clumping under the pull of gravity and the invisible scaffolding of dark matter. The first stars, called Population 3 stars, are thought to have ignited roughly 1 to 200 million years after the Big Bang. The first galaxies were expected to follow slowly, small, faint, irregular, tentative first drafts, assembled gradually over hundreds of millions of years from smaller building blocks merging together, growing through a process called hierarchical assembly. That is what the models predicted. That is what decades of theory and computer simulation told us to expect. Webb looked, and what it found was different. In its very first deep field images, taken within weeks of beginning science operations in the summer of 2022, JWST revealed galaxies in the early universe that were far too bright, far too massive, and far too well-formed for their age. These were not the faint, fragile proto-galaxies that the models predicted. They were large, luminous, and structurally mature, containing hundreds of millions of solar masses worth of stars, shining with a confidence that should have taken far longer to develop. And they existed just 300 to 500 million years after the Big Bang. The universe was barely 2% of its current age. Let that sink in. 2%. If the age of the universe were compressed into a single year, these galaxies appeared in the first week of January. There had not been enough time, according to any accepted model, for galaxies this size to form. The gas had not had time to cool. The dark matter halos had not had time to merge. The stars had not had time to be born, live, die, and seed the next generation with heavier elements, and yet, there they were, massive, bright, unapologetic. The discovery sent a shockwave through the astronomical community. Headlines spoke of galaxies that break cosmology, that defy the standard model, that should not exist. Some researchers speculated openly that the standard model of the universe, the Lambda CDM framework that has successfully described the large-scale structure of the cosmos for decades, might need to be fundamentally revised. Perhaps the initial conditions of the universe were different from what we assumed. Perhaps dark matter behaves differently at early times. Perhaps the physics of star formation in the primordial cosmos operated under rules we have not yet written. Others urged caution, and as more data accumulated over the following months and years, the picture grew more nuanced. Some of the early objects turned out to be less massive than first estimated. The initial mass calculations relied on photometry, measuring brightness in different filters, which is an indirect and sometimes unreliable method. When spectroscopic data became available, allowing more precise measurements of the galaxy's properties, some of the most extreme mass estimates were revised downward. A population of strange compact objects dubbed little red dots were found scattered throughout the deep field images. On closer inspection, these tiny brilliant red sources turned out to contain actively feeding supermassive black holes whose intense radiation had inflated the apparent brightness of their host galaxies, making them appear far more massive than they really were. A study led by Katherine Chworowski at the University of Texas at Austin, published in late 2025, showed that when these little red dots were removed from the analysis, the remaining early galaxies were not dramatically inconsistent with the standard model. As her advisor, Stephen Finkelstein, put it, "The bottom line is there is no crisis in terms of the standard model of cosmology." But the puzzle didn't disappear entirely. Even after the corrections, there were still roughly twice as many massive galaxies in Webb's data as the models predicted. Not a crisis, but a discrepancy, a persistent signal that something about our understanding of how stars and galaxies formed in the early universe is incomplete. One possibility is that star formation in the early cosmos was simply more efficient than it is today, that the first galaxies were better at converting gas into stars, that the conditions in the young universe, denser, hotter, richer in pristine hydrogen and helium, allowed stars to form at rates that would be impossible in the calmer, more metal-enriched universe we see around us now. The gas was cleaner, the gravity was stronger, and the universe, it seems, was in a hurry. In early 2025, JWST delivered another surprise. A team of researchers discovered a massive galaxy with a fully developed spiral structure, earning it the nickname the Big Wheel, that existed within the first 2 billion years of the universe. Spiral galaxies, like our own Milky Way, are thought to require billions of years to settle into their elegant, ordered shapes. They need time for the chaotic swirl of gas and merging fragments to calm down, for the rotation to stabilize, for the arms to form. The Big Wheel should not have had time for any of this. It should have been chaotic, messy, turbulent, still assembling itself from collisions and accretion. Instead, it was spinning in a graceful, ordered pattern, as though the universe had skipped several chapters of its own story. A separate study, published in October 2025 by a team at the University of Cambridge, analysed over 250 galaxies from when the universe was between 800 million and 1.5 billion years old. Most of them were turbulent and clumpy, which matched expectations, but some were already showing signs of ordered rotation, suggesting that the transition from chaos to structure began earlier than models predicted. The early universe was not the formless void we imagined. It was already busy, already building, already producing structures that, by every measure we had, should have required far more time to emerge. The implications are not settled. The standard model of cosmology has not been overturned, but it is being stretched. The early universe was more efficient, more productive, and more structurally capable than decades of simulation had prepared us for. And JWST, with its ability to see further and more clearly than any instrument before it, is the reason we know. Discovery 2, the most distant galaxy ever seen. Its name is JADES-GS-Z14-0. It does not roll off the tongue, but what it represents is extraordinary. This galaxy was observed at a redshift of 14.32, which corresponds to a time just 290 million years after the Big Bang. The light that Webb captured had been travelling for 13.5 billion years. When that light was emitted, the universe was roughly 2% of its current age. It is the most distant and therefore the youngest galaxy ever observed by any instrument. And it should not look the way it does. JD's GS Z14-0 is over 1,600 light-years across. That is small by the standards of a modern galaxy. The Milky Way is 100,000 light-years across, but for something that formed less than 300 million years after the beginning of everything, it is remarkable. It contains several 100 million solar masses worth of stars. Stars that are young and hot, burning through their fuel at a furious rate, pouring ultraviolet energy into the surrounding gas. The JWST team was able to determine that the galaxy's light is stellar, not produced by a supermassive black hole at its centre. This matters. Black holes can make small galaxies appear deceptively bright, but JADES-GS-Z 14-0 is genuinely luminous. Its brightness comes from stars, a lot of them, formed very quickly in a universe that had barely begun. In March 2025, a team using the Atacama Large Millimeter Array, the ALMA radio telescope in Chile's Atacama Desert, detected oxygen in the galaxy. This was the most distant detection of oxygen ever made, and it tells a profound story. Oxygen does not exist at the beginning of the universe. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. Every heavier element, everything from carbon to iron to oxygen, must be manufactured inside stars through nuclear fusion and then released into the surrounding gas when those stars explode as supernovae. The presence of oxygen in JADES-GS-Z 14-0 means that at least one generation of stars had already been born, had already burned through their fuel, had already died in violent explosions, and had already scattered their processed elements into the gas from which new stars were forming. All of this happened within the first 290 million years. The universe was not merely assembling its first galaxies, it was already recycling its material, already doing chemistry, already building complexity. Each record like this will eventually be broken. Webb will find something more distant, or the next generation of telescopes will. Records in astronomy have a short shelf life, but JADES-GS-Z 14-0 is more than a number in a catalogue. It is a demonstration, a proof of concept. It shows that the early universe was far more active, far more productive, and far more surprising than the models that preceded JWST had prepared us for. The cosmic dawn was not a slow, gentle brightening, a gradual fade in from darkness to light. It was a rush, a burst, a universe that woke up fast and got to work immediately, building structures and forging elements at a pace that has forced astronomers to revise their timelines and reconsider their assumptions about what is possible in a young cosmos. And JADES-GS-Z 14-0 is not alone. Webb has found other galaxies at comparable distances, each one adding to a growing body of evidence that the first few 100 million years of the universe were more eventful than anyone imagined. The universe did not wait to become interesting. It was interesting from the start. Discovery 3. And this one requires a careful voice, because it touches the oldest question humanity has ever asked. K2-18b is an exoplanet. It orbits a red dwarf star 124 light-years away, in the constellation Leo. It is about 8.5 times the mass of Earth, which places it in a category called sub-Neptunes, planets larger than Earth but smaller than Neptune. Sub-Neptunes are, as it turns out, the most common type of planet in the galaxy. There are more of them than any other kind, and yet there is no example of one in our own solar system. We have nothing to compare them to, no local reference. They are alien in the most literal sense. K2-18b orbits in its star's habitable zone, the orbital distance where temperatures are right for liquid water to exist on a planet's surface. The star is smaller and cooler than our Sun, so the habitable zone is closer in. K2-18b completes one orbit every 33 days. A year on K2-18b lasts about a month, and a team led by Niku Madhusudan at the University of Cambridge believes it may be what they call a Hycean world, a planet with a global ocean of liquid water beneath a thick, hydrogen-rich atmosphere. Not a rocky world like Earth, not a gas giant like Neptune. Something in between, something new. In September 2023, JWST observed K218b as it passed in front of its star. The technique is called transit spectroscopy. As the planet crosses the face of the star, a tiny fraction of the starlight passes through the planet's atmosphere on its way to us. Different molecules in the atmosphere absorb different wavelengths of light, leaving a chemical fingerprint in the spectrum. By analysing these fingerprints, astronomers can determine what the atmosphere is made of, even though the planet is far too distant to photograph directly. The results were striking. JWST detected methane and carbon dioxide, both consistent with a water-rich atmosphere. But the team also reported a tentative detection of something far more provocative: dimethyl sulfide, DMS. On Earth, dimethyl sulfide is produced almost exclusively by marine microorganisms. Phytoplankton in the ocean release it as a metabolic byproduct, a waste product of their chemistry, exhaled into the water and from there into the atmosphere. It is the molecule responsible for the characteristic smell of the sea. If you have ever stood on a beach and breathed in deeply and thought, "That smells like the ocean," what you were smelling was, in part, dimethyl sulfide. That sharp, briny, slightly sulphurous scent that seems to carry the essence of salt water and seaweed and life. On our planet, there is no known significant non-biological source of DMS. It is, as far as Earth's chemistry is concerned, a signature of living processes, a molecule that says, something here is alive. Finding it on another world, 124 light-years away, would be extraordinary. Finding it at all, at that distance, using an instrument that is essentially tasting starlight filtered through a sliver of atmosphere, is an achievement that borders on the miraculous. In April 2025, the Cambridge team published new observations using a different instrument on JWST, the mid-infrared instrument, or MIRI, which operates at longer wavelengths than the near-infrared spectrograph used in 2023. At these wavelengths, the spectral features of DMS and a related molecule called dimethyl disulfide, or DMDS, are more distinct and easier to separate from other atmospheric components. The team reported a strengthened detection, reaching 3 sigma confidence, meaning there is roughly a 99.7% probability that the signal is real and only a 0.3% chance it arose by statistical noise. 3 sigma is suggestive, it is not definitive. In physics, the gold standard for a confirmed discovery is 5 sigma, a threshold so stringent that the probability of a false positive drops to roughly 1 in 3.5 million. The team estimated that another 16 to 24 hours of JWST observation time would be needed to reach that threshold, or to rule the signal out. The reaction from the scientific community was predictably a mix of excitement and caution. Some researchers praised the extraordinary power of JWST to even attempt such a measurement, calling it a landmark in the field of exoplanet atmospheric characterization. Others warned firmly and publicly against interpreting the signal as evidence of life. Sarah Seeger, a planetary scientist at MIT who has spent her career studying exoplanet atmospheres, told the journal Astronomy, "With thousands of exoplanets in view, the temptation to overinterpret is strong, and some are jumping the gun. When it comes to K218b, enthusiasm is outpacing evidence." The caution is not unfounded. Recent laboratory work has shown that DMS can, under certain conditions, be produced through non-biological chemical reactions. though the yields are typically far smaller than what biology produces. The quantities of DMS required to explain the signal on K2-18b would need to exceed Earth's total natural production by a factor of roughly 20. That is a lot. It is within the range of what a plausible marine ecosystem could produce, but it is also a quantity that might conceivably arise from exotic abiotic chemistry in a hydrogen-rich atmosphere unlike anything on Earth. We simply do not have enough data yet to distinguish between the two possibilities. A subsequent NASA-led reanalysis, published in July 2025 and uploaded to the Archive preprint server, took a different approach. 3 independent teams analysed the combined dataset using Bayesian methods, each building their own atmospheric models. The study confirmed the planet's water-rich atmosphere and the presence of methane and carbon dioxide, but it found no conclusive evidence of DMS. The signal was there in some models and absent in others, depending on the assumptions used. The result was not a refutation of the Cambridge team's work. It was a demonstration of how sensitive these measurements are to modelling choices and how much more data will be needed before any firm conclusion can be drawn. So where does that leave us? In the most honest and most scientifically responsible place there is: uncertainty. K2-18b may harbour life, it may not. The signal may be biological, it may be chemical. We do not know. And we will not know until more data arrives, until the 5 sigma threshold is crossed or not crossed, until alternative explanations are tested and either confirmed or ruled out. Science does not deliver its most important answers quickly, it delivers them carefully. But what we do know, and what is not in dispute, is that for the first time in history, we have an instrument capable of detecting the chemical fingerprints of biology in the atmosphere of a planet orbiting another star, 124 light-years away. That capability did not exist 5 years ago. The question of whether we are alone in the universe has been asked for millennia. It has been the subject of philosophy, theology, science fiction, and late-night speculation. But until JWST, it was never a question that could be addressed with data. Now it can. The question has moved from philosophy to chemistry, from speculation to spectroscopy, from the realm of thought experiments to the realm of photons and spectra and signal-to-noise ratios. The data is coming in, observation by observation, transit by transit, and the answer, whatever it turns out to be, is closer than it has ever been in the history of our species. Discovery 4. Water where worlds are being born. Stars do not form alone. When a cloud of gas and dust collapses under its own gravity and ignites into a new star, the leftover material does not vanish, it flattens. The rotation of the collapsing cloud spins the remaining gas and dust into a disk, a vast, thin, rotating structure that surrounds the newborn star like a skirt. This is called a protoplanetary disk, and it is where planets are made. The process takes millions of years. Dust grains, smaller than the width of a human hair, collide and stick together. They grow into pebbles, pebbles into boulders, boulders into planetesimals, objects miles across, planetesimals into protoplanets, and eventually, after a long chaotic process of collision, accretion, and gravitational sculpting, into full-sized planets. This is how our solar system formed, roughly 4.5 billion years ago. The Earth, the Moon, Mars, Jupiter, all of them assembled from the material in a disk around the young Sun. JWST has now peered inside one of these disks, around a young star still in the process of building its planets, and found something that connects the birth of that distant solar system to the story of our own. Using its mid-infrared instruments, the telescope detected crystalline water ice in the inner region of the disk, the zone where rocky, Earth-like planets are most likely to form, not amorphous ice, which is disordered and formless, the kind found in the cold outer reaches of such disks where temperatures barely rise above absolute zero. Crystalline ice, structured, ordered, the kind that requires specific temperature conditions to form, the kind found in the rings of Saturn, the kind found in comets, the kind that, billions of years ago, may have been delivered to the young Earth by asteroid and comet impacts, carrying with it the water that filled our oceans and made our world habitable. The discovery matters because it reveals the raw materials for life at the very moment when planets are being assembled. The water is there, in the disk, in the right form, in the right place, at the right stage of the process. It does not prove that the planets forming in that disk will have oceans, but it shows that the ingredients are woven into the fabric of planet formation from the very beginning. Water is not something a planet must acquire later through luck. It is part of the recipe. We have known for some time that water is abundant in the universe. Hydrogen is the most common element. Oxygen is the third. They combine readily. Water is everywhere, in interstellar clouds, in comet tails, in the icy moons of Jupiter and Saturn. But seeing crystalline water ice in a planet-forming disk, in the region where rocky worlds are likely to coalesce, measured by an instrument sensitive enough to identify the specific spectral signature of the crystal structure, is a different kind of knowledge. It is not theoretical, it is observational. Webb saw the ice. It measured it. It placed it precisely in the disk, at a specific distance from the star, at a specific stage of planet formation. The water that may one day fill oceans on worlds we have not yet discovered is already there, frozen in the dust, mixed into the raw materials, part of the recipe from the beginning. And if water is a standard ingredient in planet formation, not an exception but a rule, then the number of potentially habitable worlds in the galaxy is not a small number. It is an enormous one. Every star with a disk, every disk with ice, every ice grain that finds its way into a rocky planet. The ingredients for life may be not rare but routine. That is what a few specks of crystalline ice in a distant disk suggest, and it is a suggestion that changes the arithmetic of everything. Discovery 5. The black holes that grew too fast. A supermassive black hole is not a star. It is not a planet. It is a region of space-time so warped by concentrated mass that nothing, not even light, can escape from within its boundary. Every large galaxy in the universe, including our own Milky Way, has a supermassive black hole at its centre, typically containing millions or billions of times the mass of the Sun. In our galaxy, the central black hole, called Sagittarius A star, contains roughly 4 million solar masses. The black hole at the centre of the galaxy, M87, the first to be directly imaged, contains 6.5 billion. How these monsters formed is one of the great open questions in astrophysics. The standard picture involves a seed, a smaller black hole formed from the collapse of an early massive star, perhaps containing a few hundred solar masses, that then grows by swallowing gas, dust and other stars over billions of years. Gas spirals inward, forming a superheated accretion disk around the black hole, radiating intensely as it falls in. The black hole grows, slowly, steadily, over cosmic time, but there is a speed limit. It is called the Eddington limit, named after the British astrophysicist Arthur Eddington, and it represents a fundamental constraint on how fast a black hole can feed. As gas falls toward a black hole, it heats up enormously, and the radiation it produces pushes outward against the incoming material. Above a certain feeding rate, the radiation pressure exceeds the gravitational pull and the black hole effectively chokes. It cannot swallow faster than the light it produces will allow. This limit means that even if a black hole has been feeding continuously since the earliest moments of the universe, there is a maximum size it can reach by any given time. The calculation is straightforward, and the numbers, when applied to what JWST has found, do not work. In 2024, Webb confirmed the existence of an actively growing supermassive black hole in a galaxy called UHZ-1, observed just 570 million years after the Big Bang, when the universe was roughly 4% of its current age. The black hole was already enormous, far too massive to have grown from a stellar mass seed at the Eddington rate in the time available. The maths simply do not allow it. 3 possibilities have been proposed, each one radical in its own way. First, the seed may have been much larger than a single collapsed star, formed instead by the direct collapse of an enormous primordial gas cloud into a black hole without passing through a stellar phase, a process called direct collapse that would produce a seed of 10,000 solar masses or more. Second, the black hole may have found a way to exceed the Eddington limit, perhaps through brief episodes of super Eddington accretion that are not yet well understood. And third, as a team of researchers proposed in a paper published in January 2026, these early black holes may have been seeded by exotic objects called dark stars, hypothetical stars powered not by nuclear fusion, but by the annihilation of dark matter particles in their cores. Dark stars could have grown to enormous sizes very quickly before collapsing into black holes that were already massive at birth. The idea is speculative. No dark star has ever been observed, but it would explain several of JWST's most puzzling findings at once. JWST has also revealed a population of strange compact objects in the early universe that astronomers have taken to calling little red dots. The name is informal, almost playful, but the objects themselves are deeply confusing. They're tiny, bright red sources that appear scattered throughout the deep field images, barely distinguishable from background noise at first glance. On closer inspection, spectroscopic analysis reveals that many of them harbour actively feeding black holes far more massive than their host galaxies should permit. The black holes are too big for their galaxies. The galaxies are too small for their black holes. The relationship between the two, which in the modern universe follows a well-established pattern, is wildly out of proportion. They do not fit neatly into any existing category of astronomical object. They are too bright to be normal galaxies, too compact to be explained by star formation alone, too red to be standard quasars, and too numerous to be dismissed as anomalies or observational errors. There are hundreds of them in the deep field surveys, perhaps thousands across the sky. One astrophysicist at the Flatiron Institute in New York nicknamed them the universe's most confusing objects. They may represent an entirely new phase of galaxy and black hole coevolution, a period in the early universe when black holes grew faster than their host galaxies, or when the relationship between the two had not yet settled into the proportionality we observe today. Whatever they are, they did not exist in our models before JWST. They are a new phenomenon, discovered by a new telescope demanding new explanations. The universe, it seems, was not content to grow its black holes slowly. Something in the conditions of the early cosmos, something we do not yet understand, allowed these engines of gravity to reach extraordinary sizes in extraordinarily short times. Webb is showing us the evidence. The explanations are still being written. 5 discoveries. Galaxies that formed too fast. A galaxy seen just 290 million years after the Big Bang, already recycling its elements. A molecule that might, just might, be a whisper of alien biology on a water world 124 light-years away. Water ice in the cradle where new planets are being assembled. The same kind of ice that may have delivered our oceans. And black holes that grew to monstrous sizes before the universe had time to make them, defying the speed limit that physics sets on their growth. None of these discoveries by themselves overturns everything we know. Science does not work in revolutions despite what headlines suggest. It works by accumulation, by pressure, by the slow, patient gathering of evidence that eventually forces a model to bend, or break, or expand to accommodate what was not expected. And JWST is applying that pressure, night after night, observation after observation, from a point in space where the sun never touches its instruments and the infrared sky is darker and clearer than anywhere near Earth. What connects all 5 discoveries is a single theme. The universe is more capable than we thought. It forms galaxies faster. It grows black holes faster. It produces the chemistry of life in places we did not expect. It delivers water to the construction sites of new worlds as a standard feature, not an exception. And it may, in at least one place that we can now observe, harbour the molecular signatures of biology. The universe is not the cold, empty, indifferent place we sometimes imagine. It is busy. It is creative. And it has been creative since the very beginning. The telescope was designed to last 10 years. It may last 20 or more thanks to an exceptionally precise launch that conserved its manoeuvring fuel far beyond expectations. The Ariane 5 rocket placed it on such an accurate trajectory that the corrections needed were minimal, leaving decades of reserve fuel. That means decades more of data, decades more of surprises, decades more of discoveries that will force us to revise, refine, and sometimes abandon the stories we tell about how the universe began, how it evolved, and whether anything else is alive in it. JWST is showing us that the visible part is stranger than we imagined, and the invisible part, the dark matter and dark energy that make up 95% of everything, remains as mysterious as ever, waiting for instruments that have not yet been built and questions that have not yet been asked. Maybe your eyes are growing heavy now, maybe the room has gone quiet, but out there, a million miles from Earth, on the cold side of our planet from the sun, a gold mirror the size of a house is floating in the dark. Its sun shield, 5 layers of Captain thinner than a human hair, is blocking the warmth of our star. Its instruments, cooled to 40 degrees above absolute zero, are counting photons that left their sources billions of years ago. Photons that have been crossing the void since before our sun existed, since before the Earth formed, since before the Milky Way settled into the spiral shape we see tonight. Photons that were emitted by the first stars, or the first galaxies, or the gas clouds that would one day become both, and that have been travelling in a straight line at the speed of light for nearly the entire age of the universe, arriving now, tonight, at a golden mirror floating in the silence beyond the moon. Those photons are arriving now, and the machine is reading them, interpreting them, turning ancient light into data, and data into knowledge, and knowledge into questions that are deeper and stranger and more humbling than the ones we started with. That is what the best telescopes do. They do not just answer questions. They reveal that the questions we were asking were not big enough. And somewhere in the data that JWST is gathering tonight, there may be a discovery that has not yet been made, a signal not yet noticed, a pattern not yet recognized, that will one day change everything we think we know. Thank you for listening to Streamberg Space Stories. If this story gave you something to carry into the night, subscribing truly helps us keep making these, and I am grateful for every one of you who does. Take care of yourself, sleep well, good night.